Okay, g'day students, welcome to our lesson on mass spectroscopy of organic compounds. So we're going to use data, mass spec data, to determine the structure of organic molecules, and then we're going to analyze data from the spectra to communicate conceptual understanding, solve problems, and make some predictions. So back in Unit 1, we looked a bit at mass spec, and we're particularly Unit 1 in the analytical techniques. Now, if we have a look at what's happening here, you can see that a mass spectrometer has got an ionization chamber. So it's turned into a gas and it's shot full of electricity, so lots of electrons. Okay, so those charge plates to provide an electric field, and what's happening here? Then there's a magnetic plate or a magnetic field at right angles, and the ones with the smallest amount of mass are going to bend more, the ones with a bigger mass are going to bend less, and that is used then to detect the mass of different particles. So looking at the principles, what do we have? We have ions that are formed in the ionization chamber where the sample is exposed to high voltages. So the ions are then separated in a magnetic field on the basis of their mass to charge ratio. The number of ions with different MZ values are measured by a detector, and the data is recorded as a mass spectrum. So let's analyze the mass spectrum of pentane here. So, whoops, get our highlighter out. So pentane, what is it? C5H12, so it's got a mass of 72. Now you can see here that, therefore, you can pretty well straight away figure through calculating it through the periodic table or interpreting the mass spectra that the M to Z value of 72 has got to be the molecular ion. Now that's the mass of the whole molecule less one electron. So remember, they've got to have a charge. They're bombarded with electrons, get a charge, and so it becomes, in this case, CH3, CH2, 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 CH3 plus. So when that charge equals 1, so the Z equals 1, the M to Z ratio indicates the mass of the whole molecule. So the mass over 1 equals the mass of the molecule. So that's the molecular ion peak. The next concept to think about is the base peak. Now the base peak has got the highest relative intensity. So that's the most abundant fragment ion. Now it's assigned the relative intensity of 100%. So all the other abundancy is a comparison to the relative intensity. So we call this the base peak fragment. And this is for the ion CH3, CH2, CH2 plus. So it's some sort of prop molecule, isn't it? So it's lost a few CH3 and a CH2 there. So let's think about how different molecules can fragment then in the mass spectrometer. So if we have a look at ethanoic acid, so what's that? CH3COOH. Now that's got a mass to charge ratio of 1, so it's got a molecular mass of 60. So we know that that's got to be the molecular ion. And the molecular ion, remember, has just lost one electron. So we say that this is the molecular ion caused by the loss of an electron. So CH3COOH plus. Now let's have a look at some of the others. So here's 45. So that's a COOH plus. So it's obviously lost a methyl group. So we've lost the methyl group from the molecular ion. And where is this one? Loss of CH3. So this is what the ion would look like here. Now let's have a look at our base peak. So that's got the highest. So we assign that the relative intensity of 100%. And remember, everything else is compared to that one. So what's happened with this? We've formed CH3CO plus. So we've lost the OH. So we've lost the OH from the molecular ion. And we've got a mass to charge ratio of 43. Now let's have a look at the next one. We've got, what is it, 42. Here's our 42. And what's happening here? We've lost another hydrogen from that again. So it's just got a mass to charge ratio of 1 less. And now let's have a look at the one at 29. So we're certainly fragmenting more, aren't we? So we've got a COH plus in this case. And that's the loss of the hydrogen from the CH3 CO, this one up here. And I think we're down to 15 now, so let's have a look at 15 finally. We've just got that methyl group left over, so we've lost, oh that's too dark, let's try a different colour. We've lost the COOH from the ethanoic acid molecule there. So that's the fragments that have formed in the mass spectra. Now, sometimes we have two different isomers. They've got the same molecular formula. So let's have a look here. We've got methyl propanoate and ethyl ethanoate. They have the same molecular formula of C4H8O2. So right up here, they should be pretty well the same. So what we're going to do is try and look for distinguishing features between the two mass spectra. And I've highlighted them in yellow and blue for you. So let's have a look at the first one, which is methyl propanoate. And we've got a fragment here at 57, and the fragment ion is just CH3CH2CO+. And then the fragment ion at 29 is CH3CH2+. Now if we look at ethyl ethanoate and charge 2 mass to charge values, what's distinguishing one in there? The one at 43, so that's a fragment ion of CH3CO+. And what else do we have? We've got a fragment ion of OCH, 2CO3, CO3, so it's over here. And then finally at 73 we've got a fragment ion of CH3COOH2, and that's A+. Now isotopes are going to have an effect. Now hydrogen, carbon, oxygen won't have a huge effect because their relative abundance of these isotopes is quite small. So you're only going to get small peaks on the mass spectra. Now let's do that one. So they're small, so small peaks, so they're not to worry about. But if you've got something like chlorine and bromine, then that's a bit of a worry. So if we have a look at a mass spectrogram of, we've got chloromethane here, we've got chlorine that has two isotopes. So we can have two molecular ions at two different mass to charge ratios. So the biggest one is the one with the biggest isotope, so it's got the chlorine 37. So that's this one here. And then the yellow one I highlighted has got the chlorine 35, and that's just going to be a little bit less, isn't it? So it also stands to logic then, if chloromethane has two different isotopes, dichloromethane is going to have three different isotopes. You're going to have what? The one with two 35s, a 35 and a 37, and a 37 and a 37. So you're going to have three molecular ion peaks. Can you do that stuff today? Can you select and use data from mass spec and what to communicate conceptual understanding, so fragmentation, etc., and solve problems and make predictions? When you're done there, please work on exercise 11.3.